I want to begin to talk about AC circuits and phasor transforms. If you have forgotten about sinusoidal functions and trigonometry, and you have forgotten about complex number math, there is a sort of prequel to this video that discusses those things, does a review, maybe a little bit too detailed, but if you find that some of this stuff is looking unfamiliar, you might want to go back and watch that video first. So this begins our sort of final unit of the class where we will discuss AC circuits and signals and the phasor transform as a way of solving those. So the first thing we want to talk about is that we do know that we can express a sinusoidally varying function with either a sine function or a cosine function. Either one of these would be perfectly fine and work equally well. But in electrical engineering, we base things off of the cosine function. And I'll talk to you a little bit more about this later in this series of videos about why we do that. But electrical engineers tend to base things off of the cosine function. So you can express a sinusoidally varying voltage with this following expression. So V is the voltage as a function of time. V sub m is referred to as the amplitude or the magnitude of the voltage, and then it is a cosine function, and inside the parentheses of the cosine function in the most general sense is omega t plus phi. So let's talk about each one of these terms. And we do refer to this as an AC or alternating voltage. So here's a plot of a sinusoidal voltage. So this is just kind of what it looks like. Sinusoidal voltages have a period. A period is how long it takes the voltage to return back to its original values. So you can see, you can define the period anywhere as long as you start at one point and then end at the next point where it repeats. So these are referred to as periodic functions because basically they just repeat with some regular time that's known as the period, which is given by capital T when this scale is in seconds. V sub m is referred to as the magnitude. It is the maximum value, and it's also negative V sub m is the minimum value. So the magnitude is not peak to peak, which would be 2 Vm. It's actually from 0 to the maximum displacement of the sinusoidal voltage. And by the way, we did say we were working with cosine functions, but we refer to them as sinusoidal voltages. The term sinusoidal is inclusive of both sine and cosine variation with respect to time. So sinusoidal does not mean the sine function. So let's go back and look at this general form one more time. So we have Vm times the cosine of omega t plus phi. You notice here's t, it's the variable. So this might look something like 10 cosine of 20 pi t plus 30 degrees. Okay, phi is the phase angle, and in this expression, we're defining it in terms of plus phi. So what I want you to note here is the plus phi inside the cosine function. What that does is it shifts the cosine function to the left. So here is where I might normally have my cosine function begin at t equals 0. What that phase shift does is it shifts the entire function to the left. So a positive phase shift will shift it to the left. A negative phase shift will shift it to the right. Okay, t is the period in seconds, and f is referred to the frequency in cycles per second, which is a term that is never used. So we will call that either seconds minus 1, or the more standard term is to call that hertz. So if t is in seconds, 1 over t is in hertz, and it represents the number of cycles per second. So once again, cycle per second is called a hertz. People never use that terminology. Now, omega represents what is referred to as the angular frequency of the sinusoidal function, and it's related to both the frequency f and the period t. So the relationship is that if f is cycles per second, there are 2 pi radians per cycle. So if we take 2 pi f, we'll get the units of radians per second. Substituting 1 over t for f, omega can be expressed as 2 pi over t. So this is a units balancing issue, knowing whether to multiply or divide by 2 pi. So once again, if you have hertz, then you multiply that by 2 pi radians, and then you get radians per second. So omega is 2 pi f. There are some textbooks that, in lieu of the omega inside the cosine function, will replace that with 2 pi f, especially in signal processing and communications. They will sometimes do that. So anyway, our omega is radians per second, and that is what we call the angular frequency. Sometimes I'll say frequency in radians per second. Once again, phi is referred to as the phase angle. What it gives us an idea of is with respect to, so in an AC signal, which is an alternating current signal, the location of t equals 0 is somewhat arbitrary. So we define a t equals 0 usually based around some voltage in the system. And then everything else, where the sinusoidal function's maximum is displaced or can be displaced. And so the phase angle is just basically a shift along the time axis. It does not change the frequency omega, nor does it have any effect on the amplitude. All it does is shift either to the left or the right. So reducing phi to 0 shifts it phi over omega time units to the right. So when compared with the sinusoidal function with phi equals 0, as we said before, if you have a positive phi, it's shifted to the left. If you have a negative phi, it's shifted to the right. So this last sentence is the thing to look at for that. So here's an example. Once again, if this is t, then the shift has units of phi over omega, and that would give you the shift in the time domain as opposed to the shift in the angular domain, which if you plotted this versus omega t, you would be plotting angles. So once again, phase shift illustrated here. Positive phase shift shifts that cosine function from having a maximum at 0 to having a maximum at negative phi over omega. So remember that you have the cosine of omega t plus phi, and so that's referred to as the argument of the sine function. Theoretically, you could plug in any time omega and phi are known, and so you could then calculate the value of the cosine function at a particular time. Now, for traditional reasons, phi is typically expressed in degrees, and omega is given as radians per second. So omega t will be radians, and phi will be degrees. So you have to do a conversion of one or the other. This says omega t is converted from radians to degrees. You, of course, could also convert phi from degrees to radians. They just have to be the same. The conversion factor is, if you're given an angle in radians, it's basically a ratio problem. So given an angle in radians, multiply by 180, divide by pi, and that'll give you degrees. Obviously, if you're given degrees and you want radians, you flip the operation. Okay, another important characteristic of the sinusoidal voltage is something we call its RMS value. I'll talk a little bit more about RMS in an example problem. Basically, you can define an RMS. It's referred to as root mean square. You can define it for a periodic function as the square root of the mean of the function squared. So if we wanted to find the RMS of Vm cosine omega t plus phi, we take the function and the first thing we do is square it. Then we integrate it over a period and divide by a period, and what we're doing there is finding the mean. Once we have squared the function and then found the mean, we take its square root, and that gives us root mean square. So to find the root mean square, you actually do the calculation in reverse. You do square, and then you take the mean, and then you take the root. Root mean square voltages are important because if you look back, let's just go back a few slides. We'll just look at this one. You can see how this voltage oscillates. And if you just look at the solid line, you can see how the area above the V equals 0 line and the area below the V equals 0 line are equal. So if you were to just take an average of this function, basically that would give you a voltage of 0, an average voltage of 0. So that doesn't tell us anything about what the actual circuit is doing, because remember, in circuits what we're interested in usually is delivering power to a load. So if you're delivering power to the load, as you know, when you go home and plug some appliance into your AC wall plug, you get power. So rather than find the average voltage, in order to understand what power we get out of the system, we work in RMS. And what that does, what the RMS will do, is it'll give you like an effective DC voltage. In fact, some textbooks refer to this as V effective. That's unusual, but it does. I have seen it before. Okay, so this is the formula. This is only the formula if there is a cosine function. If the voltage were given by some other function, then this function here that's inside the integration would be different. It would be whatever our function was. But since we're talking about AC signals, we're showing this one. If you do that integral and you do that calculation, you find that the root mean square voltage is equal to whatever the maximum, the amplitude or magnitude of the voltage was, divided by the square root of 2. And by the way, VRMS is not a function of time, because in the calculation, when you found the mean, you actually averaged out the time variable over a period. So it's not a function of time, it's a constant. So once again, the RMS voltage represents like a DC equivalent from a power perspective of a voltage with a magnitude Vm. Okay, so let's just look at an example. So a sinusoidal current has a maximum amplitude of 20 amps. The current passes through one complete cycle in 1 millisecond. The magnitude of the current at t equals 0 is 10 amps. So we're asked several things. We're asked first, what is the frequency of the current in hertz? Then we're asked, what is the frequency in radians per second? Then we're asked to write an expression for I of t using the cosine function. And we're asked to express phi in degrees. And then finally, we're asked what is the RMS value of the current. So let's look at what we're actually given. We're given the magnitude, 20. We're given the period, which is 1 millisecond, or 1 times 10 to the minus 3 seconds. And then we're told that at t equals 0, the magnitude is 10 amps. So what is this telling you? This is telling you how to calculate the phase. So let's go back one more time and look at this formula. So if you're given the value of V when t is equal to 0, okay, if you plug 0 in here for t, then what you have is V is equal to V magnitude times the cosine of phi. So if you're given little v at t equals 0, and you're given V magnitude, then cosine of phi is your unknown. And so you can solve for the phase angle. So that's what that question is actually asking you to do. So now let's go to the next slide, and we'll jump back and forth here. So first of all, in order to find the frequency in hertz, we take the period, which is 1 millisecond, and we'll express that in seconds, 0.001. That's important not to lose track of your millis. So we take 1 over t, and we end up with 1,000 hertz. To get omega from that, we multiply 1,000 hertz by 2 pi, so we get 2,000 pi radians per second. Once we have found omega, we can plug in the things that we know into our general form. So in order to find an expression for the current, you're working with this general form here. Okay, this is our sinusoidal current. Notice it's got the cosine function, it's got omega t, it's got phi, and it's got the magnitude. So we were given the magnitude. I won't flip back. Hopefully you can remember that the magnitude was 20 amps. We were given the magnitude and we calculated omega. So what we still have to calculate is phi. So we were told once again that at t equals 0, I at 0 is equal to 10 amps. So plugging in 0 for t, we have 10 is equal to 20 cosine phi. If you solve that for phi, taking the arc cosine, then you get 60 degrees for phi. So plugging that into the general expression, we now know everything we need to know about this current. And so we have an expression for the AC current in this circuit. Now the RMS value, because this is a cosine function, the RMS value is going to be the magnitude, which is 20, divided by the square root of 2. So the RMS value is going to be 14.14. And let me see, I think I maybe reversed these two slides. Did I? Maybe not. Let's skip over this because I'm not sure what I was looking at. Okay. So let's look at this one now. This is asking you, this is a little bit of a different question. They're asking you to find the RMS value of the current, and we have a graph for the current. So the first thing to do is to identify the fact that, we reach one period right here. And then remember what we do when we find the RMS value. We square the current, and then we take its mean. So that would mean that I would have to get my pointer, my pen here. That would mean that I would have to take this function from here to here, square it, and integrate from 0 to t over 4. And then I'd have to take it from here to here, square it, and integrate from t over 4 to 3t over 4. And then I'd have to write an equation for this line from 0 to t. However, notice that basically this is the same function. It's just one segment of it has a negative slope. So if you were to square this, and remember what the RMS is finding. It's actually when you integrate, you're finding the area under a curve. So if this is squared, it all becomes positive, and the area under the segment of this function squared from 0 to t over 4 is going to be the same as the area here and the same here, because when you square it, remember it all goes positive. And the same here. And the straight line is going to look kind of like it's going to look parabolic, because it'll be, instead of proportional to t, it'll be proportional to t squared. So you're going to have these spiky things. But really, if you calculate the area under the curve, or the integral for one segment of this, just the first 1/4 of it, then you just multiply it by 4, and that'll give you the area for all of it. So let's look at that. So here is the general formula. Okay, we talked about how the formula 1 over the square root of 2 is only accurate for the cosine function. So this is not a cosine function. So we're going to work from the definition of the RMS, which means we take I and we square it and we integrate it over a period, and then we divide by a period after it's been integrated, and then we take the square root. So we're going to do that with this function, and we're going to do it only, we're going to do the integral only for the first quarter of the period, because that's what we were looking at in the previous slide. So here's our I squared, and we're going to say that the integral from some t sub 0, which is our starting point, which in our problem would be 0, to over t sub 0 plus a period, that's going to be 4 times the integral over 1/4 of a period. Now you cannot do this all the time. We can do it in this problem because of the symmetry in the problem. This is not something you can do for every problem. There are occasions where you would have to break it up into multiple segments and do the integration, but in this particular case, no. All right, so if we take the integral of I squared dt over t over 4, we come up with the RMS value of IP over the square root of 3. So let me see if I can't get that a little more clear. I'm going to need to come out of slideshow and kind of select some things so that you can see the calculation a little better. And now let me go back to slideshow. Okay, so we take this fourth of an integral and we get 4 times IP over big T times little t. And this is the equation for the line. So the equation for that line is the slope times t. The slope is 4IP over t. I'll let you go back and look at the curve so that you can see that. It's a positive slope. That's the equation for the line that runs from 0 to t over 4. We then integrate that. So here we are. We take I and we square it, and then we integrate it. So the constant comes out. We still have our 4. When we integrate t squared, we get t cubed over 3, and then we run that through the limits from 0 to t over 4. And when you do that integral, this is the result that you get, IP squared times t over 3. Now, according to the formula, we multiply that by 1 over t, and so we get 1 over 3 times IP squared, and IP, remember, is the magnitude. We then take the square root of that to get the RMS value. So you take the square root, you'll get the peak current divided by the square root of 3. So I want you really to work back through this example that we've just been over and be sure you understand how to do this, because I almost always put at least one RMS problem on the exam over AC. Okay, so I'm going to stop the video here and we'll pick up with the next slide on the next segment of videos.